2 is 10 to the negative 23rd. Fascinating. Oh, hello. My name's Matt Glover. I'm the SATCOM engineer here at Palmer Station. Today, with a little help from some friends of mine, I'd like to tell you how to stay safe around RF equipment. But first, you might be wondering, just what the F is RF anyway? Here's someone to explain.
Radiation. It's when energetic particles or waves move through space, and it's pretty much the best thing ever. Radiation includes visible light, which is always bouncing off of stuff and then hitting our retinas, allowing us to not stub our toes and generally enjoy the splendor of the world. It's also what plants convert into the food we eat. Infrared, or IR radiation, which is this stuff that actually warms the Earth, so it's the reason that we're not all freezing to death right now. Microwaves, which not only heat up our hot pockets, but also transmit our cell phone calls. A huge amount of study into whether these microwaves cause cancer indicates that they probably do not, and the World Health Organization classifies them in the needs more study category, along with coffee and pickled vegetables. Radio waves, which carry, yes, radio signals, also 3G and Wi-Fi and all that good stuff. And then we have the extremely low and very low frequency waves, which aren't super useful but don't hurt anybody either. Unlike all of the above examples, some kinds of radiation can transfer their energy into atoms and ionize them, removing electrons, which is where the problems begin. When most people think of radiation, what they're really thinking of is this radiation, which is ionizing radiation, including X-rays that can ionize atoms, but it's generally worth it to take a peek at your broken bones. Ultraviolet radiation, which is mostly non-ionizing, but can excite atoms enough to cause some unwanted reactions, like in our skin, which is why we put on UV protection in our sunblock. Gamma rays, which are pretty much the worst kinds of all the radiations because they can travel through pretty much any material and then ionize an atom right out of your DNA, leading to some pretty serious problems.
Thanks, Larry. As he just described, there are many types of RF radiation, but why should you care about it? Mostly because it's all around you. And it's useful. Here's Larry to tell you more.
Can you imagine what life would be like without a cell phone? They make things so much easier and a lot more efficient. The problem is the signal has to get where it's going without wires. That's why you see so many telecommunications antennas everywhere. And believe me, there are more coming, lots more. Workers do a ton of work on building rooftops, sides of buildings, and mobile news trucks, popular places for telecommunications antennas. So, are you safe working near these antennas? You may be.
RF is the energy used to provide cell phone and other telecommunications services, such as satellite communications, television broadcasting, and portable radio communications, without wire. It's not harmful if you're far enough away from it, but if you're close enough to it for a long enough period of time, you could have a problem. You know how when you cook something in the microwave, the energy penetrates into the food, making it hotter and hotter the longer it's exposed? That's what could happen to human tissue if it's overexposed to RF radiation for a long enough period of time.
Microwaves are great for chemistry as well. In fact, regular old microwave ovens have been used in chemical synthesis for years in academic labs.
Now when it comes to actually cooking food, there's still a lot left to be desired. I mean, it's been over 70 years since the first microwave ovens, and yet the new ones aren't any more powerful. What gives? It turns out, the people who make these things have been feeding us lies for years.
So hear me out. What happens when you use the 50% setting for slow cooking? Any self-respecting person would expect the oven to simply run at half power, but check out that power draw. What actually happens is that the oven runs at full power for an amount of time, then turns off for a while before repeating the cycle. Sure, it averages out given enough time, but it's still dirty.
Now, admittedly, that one's not that big of a deal, but it does lead us to the lie that's downright disgusting.
What happens when you use the 100% setting? Most people don't question this setting because it's all they've ever known. But let's take a look at what that looks like in slow-mo. See how they flash like that? Yeah, that's right. Even at the 100% setting, the bulbs are only on half the time, and this is because the oven is only producing microwaves half the time. What a scam!
Alright, so I've taken this thing apart to expose the circuitry inside. Now I gotta say it, poking around in a microwave is not for the inexperienced. Anyway, here's the reason why the oven's only on half the time.
So this magnetron here, which is actually the source of microwaves in the oven, is powered by feeding the output of this high voltage transformer into this halfway voltage doubler circuit. Now the very nature of the circuit means that the magnetron is only going to be powered on half of the AC cycle.
Now if the transformers in these things weren't ran so ridiculously close to saturation, you could just throw in another capacitor and diode to make the full wave doubler and call it a day. But you can't, so that means I have to sacrifice another microwave for the transformer.
So a cup of water heats by about 28 degrees Celsius in a minute, which also suggests about 40% efficiency. Now obviously, this isn't quite fast enough for my liking. I went ahead and unlocked full power mode here. I've added another transformer, as well as some more diodes and capacitors to make the full wave doubler circuit. But wait, won't a microwave using double the power trip the breaker? Well, it's nothing a little bit of copper wire and duct tape can't fix.
I was too lazy to use the original controls on the microwave, so now I'm using this huge variac to power it.
A benefit of the new setup is that it bypasses all of the safety mechanisms, which means the oven door doesn't even have to be closed for it to operate. I was curious how a camera would react inside my Faraday cage with the open oven. Let's go ahead and redo that water heating experiment with a full power microwave. The original microwave drew a little under 1200 watts, so I'm going to dial the power to about 2400 watts this time. Over the course of a minute, the power draw actually increased to about 2800 watts, probably due to the toasty magnetron filament spitting up more electrons as it heated. The full power microwave heated the water way faster this time, 63 degrees Celsius in 1 minute.
So, now that you know what a simple microwave oven can do, you might be wondering, how does a magnetron, using a little over 2 kilowatts of energy, compare to the amount of RF energy produced by the devices here at Palmer? Just how cooked are my insides? And for that matter, what the heck are all those antennas anyway? For answers to those questions and more, come along with me on a journey of discovery.
This towering structure is the West Rhombic Tower, otherwise known as the VHF Tower. It houses many antennas used for all sorts of communication around the station. At the top of the tower here is the dipole loop for channel 27. A little bit below that is the loop for channel 16. Further down is the webcam. A little bit below that, right here I think, is the weather broadcast that you can hear on your radios when you hit the weather button.
Whoa, 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 whoa. Hang on just a minute, Matt. That's a lot of information about what comes out of these antennas, but nothing about the danger. Also, saying dipole loop might be an oxymoron, and I might have said it a lot in this video, but we won't worry about that right now. Anyway, how much power comes out of one of these handheld radios anyway? And how much power comes out of the repeaters? The answer might surprise you. The ICOM M73 radios are capable of transmitting in 3 different power levels. These are referred to as high, indicated by no indication, medium, indicated by the word mid, and low, indicated by the word low. They can also play a little tune. The output power of the transmitter in low power mode is 1 watt. The output power of the transmitter in medium power mode is 3 watts. The output power of the transmitter in high power mode is 6 watts. Fascinating. While 6 watts out of these things is respectable, sometimes it's just not enough power to get us the range that we need. So that's why we use repeaters. The repeaters connect to amplifiers, which are then in turn connected to the antennas on the tower you just saw. The repeaters can amplify a signal up to 30 watts. Wow, that's a lot of power.
Hey, look at this. How you like that, huh? It's really lighting up, see? No, it's not even plugged into anything, is it? No. But see, I'm using my radio. I'm transmitting with my radio. See my antenna? See? As it gets closer, the radiation from the antenna is lighting up the bulb. Hey, well, there you go, huh? So, yeah, my walkie-talkie, you know, it's about 5 watts on VHF. You could do it on UHF as well. And the electromagnetic energy charges the gases in the fluorescent bulbs.
Wow, thanks Larry for that amazing demonstration. How cool is that? Now, let's resume our journey of discovery and look at some more of the RF equipment here at Palmer.
Behind me is the conical monopole antenna. You can tell it's the conical monopole antenna because of the way that it is. This antenna radiates in an omnidirectional path that corresponds with the horizon. It's good from a frequency range of 3 megahertz to 30 megahertz. It is sometimes connected to an amplifier that radiates with energy up to 2 kilowatts. It's currently inoperable, but you should still stay away from it nonetheless. Here you see the tower that the Sloping V antenna is attached to. You can tell it's the Sloping V antenna because of the 2 dipole elements that come from the top of the tower that make a V shape. This antenna is a directional antenna that's used for long-range communication back towards the United States. It operates at a frequency from 4 to 30 megahertz. This antenna can also sometimes be connected to an amplifier that puts out up to 2 kilowatts. But not to worry, as long as you don't touch any of the radiating elements, you should be fine. You should be. Attached to the same tower as the Sloping V is the INVIS antenna. You can see one of its radiating elements there. This antenna radiates in a very limited frequency band around 4.1 megahertz. It radiates straight up. Its signal bounces off the ionosphere and has a range of 300 to 400 miles. If you're watching this video in the future, chances are it might even be repaired.
Follow me as we gain access to and identify some of the radiating elements on the Biolab antenna tower. Right this way, come on. As you can see, the Biolab antenna structure is accessed through the specialized hatch. While most of the antennas attached to the Biolab tower are passive devices, it does contain a few active elements, such as the antenna attached to the FM transmitter. Shout out to Chris Perry as our only listener. It also contains antennas for the GPS, the Iridium phone, and several other test antennas that provide a means of testing various signals around the station, linked directly to test equipment in the communications office. And now the moment you've all been waiting for. What is inside of the radome? So this is the backside of the satellite dish that provides our internet connection to the SES-14 satellite. It transmits at a power level of 140 watts. It receives at a level that's probably in the microwatts.
No matter how many antennas are present, or what types of antennas we're talking about, it's difficult to determine exactly how much RF is being emitted at any one time unless you have an electromagnetic field monitor to measure it.
That's because there's no other way for you to know the power and frequency of each antenna in the area at the exact time you're working.
Frequency matters when it comes to health effects on humans. Frequencies between 30 and 300 megahertz appear to be the most harmful because that's the range where humans absorb RF most efficiently when they're in an RF field, but still some distance away from the antennas.
One way to protect yourself is to stay out of the RF field altogether. That's the area through which the RF is being emitted. So, when in doubt, distance is your best ally. RF dissipates considerably, losing its potency the farther it travels away from the antenna. So, the farther away you are from any RF source, the less your risk of overexposure.
The bottom line is, if the antennas are far enough away from your work area, or if they're emitting the RF in a single direction away from it, there's no problem. Just carefully choose your access route to and from the work area to avoid or limit your exposure. There are 3 other key considerations you should know about. The first is that active RF antennas are extremely hot. If you were to touch one, you would experience some pretty severe burns.
But that should never be a problem if you're following these safe work practices, because you'll never be that close to an active antenna. The second consideration has to do with pacemakers.
Now that you've gotten a closer look at some of the RF equipment around Palmer, hopefully you'll be able to stay safe and identify what is dangerous and what isn't. Keep in mind, I've only pointed out some of the hazards. I suppose you'll have to find out about the rest through trial and error. Maybe it's the Wi-Fi access point. Maybe it's the Bluetooth signal pumping up your jams. Or maybe it's the warm, cozy fire in the galley. If you have any questions or would like any additional information, feel free to look it up on the internet. That's what I did. In any case, I hope you have a wonderful evening and thank you for coming to this mandatory briefing. Goodbye!